Okay, so let's, what do we do? I hope someone wrote that stuff down. Okay, but what I'd be doing is trying to collect, trying to collect the terms into a W transpose A W style term and a B transpose W. So in some sense, well, let's write the form we're going for. It's something like that. This is actually the thing that we've just been writing down, because we've collected all those terms into an A and a B, where we've said that A is equal to alpha minus 1I. It's amazing I can remember this stuff. Look, this is because I dream about these covariance functions. Yeah? So where A was that, and B, correct me if I'm wrong because I'm doing that from memory, and B was, so let's put half in there, yeah? This is the way we've written it. And B was sigma to the minus 2, yeah? Sum of I equals 1 to n xi, so let's call it like ti xi transpose t. Sorry. Ti, not w. Confusing myself. We want it in this form. Call it mu w just to say the mean of w, the posterior mean. C is what we often use for covariance, inverse C. We want it in that form because that's what we expect the exponential of the Gaussian to be. Once we've got that, we know the mean, we know the covariance, and the other bits of the Gaussian out the front that are 2 pi to the p, where p is the dimensionality of x, the size of the input space, determinant c to the half. But we don't, that's there all the time. Once we've got it in that form, we know that's the normalizer. So we're trying to get it in that form. We're trying to match that to that. Yeah, and decide what C is in terms of A and B, and what mu is in terms of A and B. Now, one little way of doing this is to just multiply out on the bottom. So this thing here, W transpose C minus 1, with a half in front, W. That's the first term. W transpose C minus 1 times W. That's the first quadratic term. Second term, minus mu W transpose C minus 1. W. And then we also get a W transpose C minus 1 W mu minus. So that's a W transpose C minus 1 mu. And then the last term, minus mu W transpose C minus 1 mu. No, I missed out the half, sorry. We're trying to match this to this. Something's emerged already. What's the quadratic term in this? First term, yeah. Let me make it slightly easier for ourselves. Just put a minus half in there. If we put a minus half on here, oh, I missed them. So I've ignored that minus on here. Crap. Sorry. That's one's right. Minus half W transpose C minus 1 W matches to minus half W transpose A W. So A is what? Equal to what? C inverse is equal to A, so C is equal to A inverse, yeah. So C is equal to A inverse. So that implies, since this implies that C minus 1W is equal to A, which in turn applies that CW is equal to A minus 1. From the above implies, I've moved that half now from there to there, sorry. That CW is equal to alpha minus 1I plus sigma squared, sigma minus 2, sum of xi transpose to the minus 1. So the covariance of the posterior is equal to the inverse of this term. Yeah? CW. So everyone up to speed with that, because I read that quite quickly. Hands up if... Are we happy to carry on with that now? So we've matched the quadratic term now. Yeah? What term do we need to match now? Linear term. This term we can ignore because it's constant and we're not worrying about any constant terms, but we need to match the linear term. We can always create and destroy constant terms at will. So the linear term is actually in two parts at the moment, a W and a W transpose part. Can anyone spot how I can combine these? Using a trick we use quite a lot for... These are scalars, right? So they're in matrix forms. And the transpose of a scalar is a scalar, right? What's the transpose of this? If I transpose this term, can anyone remember? Remember the rules are AB transpose is equal to B transpose A transpose. So if I transpose this, what do I get? Yeah, flip it round, yeah. So flip it round, but I can't just flip it round. If I flip it round, the first term is going to be mu, but is it mu or is it mu transpose? Second term is going to be CW minus 1 transposed. Now, C minus 1 is a symmetric matrix. It's the covariance. So its transpose is also C minus 1. W. Which is just the same as that. So the linear term is basically the sum of these two things. Yeah? It's mu transpose covariance inverted is the equivalent of B. I'm going to tap that for a bit. Okay? So in other words, B, this implies that B is equal to, so B transpose is equal to that, so B itself is equal to C minus 1. Sorry, mu, don't I? Yeah. Yeah, well, let's do it this way. CW minus 1 mu, which implies in turn that mu is equal to CWB. B is this, maybe. So I don't need that bit. That would be B. B is this. So,
sorry, Camille, what did you just do then? You transposed the linear term.
yeah.
Just one of them, not both of them.
I transposed one of them just so that I could add it to the other, because once it's transposed, they're identical. Yeah. And then once I'd got them together, the two linear terms together, we identified what B was, and now we're rewriting that as mu. So the mean is equal to the covariance times B. We've already got the covariance. It's the inverse of this thing here. So let's just keep writing it as the covariance and just say that the mean is equal to the covariance times, what have I got there? Sigma to the minus 2, sum of Ti, xi, I equals 1 to n. So that's the mean. And that's Bayesian inference. I've decided not to show you how to do the marginal likelihood because we've taken too long doing the other derivations. And in effect, if I don't show you the marginal likelihood, I have shown you two derivations. Yeah, I've shown you the Bayesian solution. I've shown you the maximum likelihood solutions. They're very closely related. The ones I care about are the multivariate derivations. Yeah? You do need to know what the marginal likelihood is. You could work it out. You need to use something called the matrix inversion lemma. It actually turns out to have a really nice form. Marginal likelihood turns out to be a Gaussian. Well, we'll come back to it perhaps. It's got a really nice form. And that will lead on to, when I come back, I'm going to disappear for 4 weeks. And when I come back and give you the sort of advanced lectures, which builds on this material, but I'll wave my hands a bit and say, well, you now make infinite basis functions and do funky stuff, and then you can do some really interesting things. So it'll be stuff that I want you to know that exists rather than examine you on the details of. The marginal likelihood's at the core of everything for that material. This material called Gaussian processes. But for the moment, we'll leave it at that and suffice it to say that the posterior is this form with CW equal to alpha minus 1i plus sigma minus 2 xi transpose. You need the marginal likelihood in the lab as well. But I'll just give you the result rather than derive it. And mu equals CW xi ti sigma minus 2. Okay, so you follow that derivation. So what did we do? We expanded out the square. We took those two densities, multiplied them together, which meant adding the exponents. And then we expanded out that quadratic form. Yeah? Then we collected the quadratic and the linear terms. And then in order to match them to the Gaussian, I mean, you can remember these formulae. You don't need to, you need to know how it comes about. But I just sort of went through expanding out the form we wanted and matching the quadratic terms in. I spent a bit of time explaining why we can drop the constant terms. Alan?
Didn't you miss sigma squared?
I did, but I put it in sneakily afterwards, yeah.
Oh, right. So
Yeah, so I did forget it when I initially wrote it down, but I put it back in. It could actually appear in the front there, sigma minus 2. Oh, yeah, there was one thing I wanted to... no, I think it's in the later slides. So. Bayesian methods are really exciting. And I hope to persuade you of that by revisiting that polynomial example we looked at last time. So, are we on the right slide? We need the next slide. Oh. So what problems did we have with the polynomial fitting? Problems that you looked at in the lab with the polynomial fitting to the Olympic data. Anyone? While I'm getting this up. What problems could we have when we tried polynomial fitting to the Olympic data? Yeah, overfitting. So what I want to do now is I want to take that polynomial data, and instead of doing maximum likelihood fits, we're going to do what you do in a Bayesian approach. What we do is we choose a prior, W, and I've just selected arbitrarily the variance of that prior to be 1. And I've selected the noise to be, the variance to be 0.01, means the standard deviation is 0.1. Okay? So standard deviation of 0.1 for the noise and a variance of 1 for the Gaussian. Now, it's always useful to perform a sanity check and sample from the prior before observing the data. So that's one of the things you've been doing in the lab. Just sample a bunch of W's from the prior, yeah, and then multiply it by the phi. That's actually, in the Bayesian approach, that's what you're saying is your belief about the functions before you start. So this is one of the tasks that was in the lab in preparation for this. But what we can do now is we can make our fit to the data. And this is the 0th order polynomial, matching the one before. But we don't just have the mean. We have a variance either side that comes about from our uncertainty about what that mean was. So that's what that's showing there. The middle line is the fit. The two standard deviations either side are the standard deviations of the fit. Since there's so much data, it actually is really confident about what the mean of the data should be. And since I told it the noise was small and we're not learning the noise, it thinks the noise is small. So it's not a very good fit, actually. And what I'm showing you here is the marginal likelihood. That's the probability of this model. So this is the probability of the data with the parameters marginalized out. I haven't shown you the form of that, but that's what we're going to use in Bayesian inference for model selection. And you're asked to compute this for the radial basis functions in question 3. As we increase the model order, okay, this is fun, because now you can see the shape of these error bars. This is the linear fit, but there's uncertainty about what the gradient should be and the offset. So although the noise is still small, the noise should only be 0.1 in this fit. The uncertainty in the gradient and the offset means that you get these sort of error bars. Isn't that nice? Look, it starts fitting where the data is. As we move away from the center where it becomes more confident, it becomes less confident at the sides. And the marginal likelihood is much better. Now, as a reminder, what we saw when we looked at the training error for maximum likelihood, what happened to the error as we increased the model order? For the error or for the?
The error decreases, but then if we go on implementing the polynomial order, it gets...
Only for the validation error. If we looked at the training error, do you remember what happened with just the training error? Just went down to 0, yeah. So you're right for the validation error, but the training error, and this I'm plotting is just based on the training data. There's no validation data here. It's the marginal likelihood on the training data. So our expectation would be that the same thing would happen, that this would drop down to 0. So this is the cubic fit, sorry, quadratic fit. And look, there's uncertainty here causing it to go flying up at the side. So this is all coming from the posterior weights, this uncertainty. It's uncertain what the quadratic coefficient should be, and there's correlations between them. Here's the cubic. Uncertainty again. Quartic. Look at how big the uncertainty comes as you leave the data. This is really nice now because the quartic's quite a flexible model, but as you leave the data, it's not being determined. So as it flies out of the data, look at the error bars going up and down. It would be the same that side if we pushed further on that side. Yeah? So it drops down with the mean, but it also says, I don't really know. I have no idea what happens beyond this regime. This is the sort of behavior you want because it's extrapolating. It shouldn't really be confident about what happens beyond that regime. But also look what happens to the marginal likelihoods. Third order model, fourth order model. So this is negative marginal likelihood, just to keep it the same as an error we've been looking at. So we want to minimize the negative marginal likelihood. The smallest one is for model order 3. It starts going up again. Not massively. So there's not much difference, according to this model, between the cubic, the quartic, and the quintic. It's selecting the third order model. So the marginal likelihood doesn't necessarily always increase as the model order increases. So the negative marginal likelihood got larger, but the marginal likelihood would have been getting smaller as we increase the model order here, unlike the training error. So we can use the marginal likelihood for model selection. And the reason is the marginal likelihood has this form. Once you've got rid, so we haven't proved what the marginal likelihood is, but it's actually the probability of t given x comma sigma squared comma alpha, this is the marginal likelihood with the w's eliminated, is equal to 1 over 2 pi to the n over 2. I'm going to call the covariance matrix K. It's got a lovely simple form. T transpose K minus 1 T, where K turns out to be equal to X, where X is our input data, X transpose plus sigma squared I times alpha at the front. Very simple. So I shouldn't use X, should I? Because we're actually using basis functions here. So let me use phi. Rogers and Girolami use phi. Use X for where I use phi, has this form. So this is the thing that you've computed for the basis functions. And this is an n by n matrix, where n is the number of training data. So it's an n by n covariance, giving you correlations between the training data. And this is the thing we're computing here. It has 2 parameters in the model we've set up. It doesn't matter what phi is, the way we've set up the models, it always has 2 parameters. So it doesn't overfit in the way that the maximum likelihood did, because we got rid of all those parameters with the probability distribution. It's just a model with 2 parameters to fit the data. This parameter is the noise variance. This parameter actually controls the signal variance. So it just has a noise to signal, basically. And in this example, you can learn them, and that's what we typically do, say in my research group. But in this example, I've just set them like this, that this signal variance is 1 and the noise variance is 0.01. So the ratio of signal to noise is about 10 to 1. It's not quite true for the polynomial setup because the polynomials don't have a fixed variance in phi transpose, but that's the intuition, that this is controlling how much is signal, how much is coming from the model, yeah? And the other term is controlling how much is coming from the noise. Makes sense when you think about it, because what we're saying, you know, our overall philosophy is that T is equal to W transpose phi plus epsilon. The prior over W is controlled by alpha. How big W is controlled by alpha. How big epsilon is controlled by sigma squared. Turns out you can write down, using knowledge of multivariate Gaussians, you can write down that formula directly from this equation if you know what you're doing. It must be true because this is fixed, non-Gaussian, this is Gaussian, and sum of Gaussians is always Gaussian, that's Gaussian. So you know the end result has to be Gaussian. You can write it down directly, but we're not going to go through that. So we've said that a priori for that signal and that noise, and now we get these fits. And it says, well, if that's the right signal-to-noise ratio, which is one that I think is probably OK, 10 to 1 or something around that order, that's fine. So remember, but there's something else that goes on. Keeping this W small through having a variance over it is important because it does something to the coefficients. The prior says these coefficients must not go too large. The prior says I'm Gaussian with variance of 1. Yeah? That means, okay, let's remind ourselves of the validation set for maximum likelihood. So this is the maximum likelihood fit with a validation set. These were the pink points here. So this is, we go through and look how quickly. So this scale is going to be the same as the next scale you'll see. We do all right. I mean, we do not well, but it's a pretty good score compared to the later ones that come. We do better. On this scale, we're doing better. Oh, quadratic's already worse than... So under this validation error, remember we chose the model with order 1. Which is a bit worrying because we've chosen the model order 3, but we talked about extrapolation a bit. But then when we cross-validated, we chose the model order 3. What's going on? What's going on? OK. And then look, that's already terrible. And this one's so bad, it's off the scale. But the Bayesian fit, the Bayesian mean isn't the same as the maximum likelihood fit. We're going to show that briefly at the end. Here's the Bayesian fit, again only done on this part of the training status. So now we're using this as validation, and I'm showing the validation error here. Very similar performance, yeah? Would be. There's the linear fit. OK, the linear one actually turns out to be worse. But look at these guys. The third order fit. Wow. It's actually quite hard. I mean, it seems like the third order and the fifth order model are doing better. And this is because of crazy behavior of polynomials. So you get this sort of variance in what they're going on. But bear in mind this plot before. By third order, we were already well off. We were flying through the ceiling. But under the Bayesian model, all these models are pretty good. Yeah? Even the sixth order. Why is that? Because the prior distribution regularizes the coefficients. It says you must be small. What happens in the maximum likelihood fit, certainly with polynomials, they're not good things to fit with. The basis functions you're using, the radial basis functions are much better. With polynomials, you end up with coefficients of the order 1 times 10 to the 3. In order to just squeeze the polynomial around a certain data point. The prior says you're not allowed to do that. So with a polynomial fit, you might have, you know, x squared times 250 minus x cubed times 400, or something like that, in an effort to fit the data. W says, in this case, the prior over W says you're not allowed to do that. We expect W to be in a small range. That means that none of these bases can suddenly dominate. These polynomial fits are composed of like, or not these ones, but these ones. Yeah, look how ugly that one is, yeah? It's composed of some nasty quintic plus some nasty quartic going in the opposite direction in order to get these bends in order to bend through the data like that. It's got a very high coefficient on some of these basis functions. Regularization says you're not allowed to do that. So this is the equivalent fit under the regularized Bayesian model. Where's that twist? It's not there anymore, is it? It doesn't go flying down through there and then up there. It's just averaging, because it's averaging over a large number of well-regularized polynomial solutions. And what you're seeing is the mean of that average and the variance of that average. I'm going to do a little bit on the board about how we compute that, because you're also going to be asked to do that in the... Oh. In the lab. Okay, so bear in mind that was on the same scale. And all the fits are much, much better under the Bayesian approach. So what's happening there? Well, it's nicest to look at the maximum likelihood solution. Ooh, what have I got at the top? Oh, whoa. I've got an error there, sorry. this part here is supposed to be sigma to the minus 2 in both cases, not sigma minus 2. It looks like sigma minus 2 phi. I've accidentally dropped this down. So it's sigma to the minus 2, sigma to the minus 2. Apologies. Let me just have a go at it's so ugly, I'm offended by it. What's this slide called? Yeah, I've just missed that off. Okay, sorry, 1 second. Let's see if that works. Oh, good. Okay. This is the mean solution we've just worked out, yeah? The one that you've been writing down. What I want you to look at, the mean solution, is what happens if you make alpha, the variance of the prior, very, very, very large. So looking in this formula here, what happens to that term if alpha is large? Large alpha, 1 over alpha is small. So for very large alpha, this term does what? Disappears. So it actually looks similar here. I've left in, these guys can cancel. So since while we're at it, I'll see if I can animate my slides. I've left in the data standard deviations, but in reality, of course, sorry. The sigma squared, that term disappears. Sigma squared can move in the matrix inverse if he flips upside down.
Sorry, what's the bottom equation?
This is the maximum likelihood solution that you've been using in the labs. Yeah? Sorry, I didn't make that clear. That's the Bayesian solution for the mean. And I think the one thing I've missed out, it's in the books, but I'll just touch on, is how we're computing the mean of the output of the system. Sorry, where that bit of light is mu w. This is the maximum likelihood solution for w. If the prior is infinite variance, the two solutions coincide at the mean. But in that case, you lose this regularization effect. Remember we talked about how if you've got one data point, you can't fit these models, yeah? Well, in one data point, this basis phi consists of 1 and x. So it's a 2 by 2 matrix, phi transpose phi, yeah? It's a 2 by 2 matrix, but it's only made up of one observation. 1 and x transpose times 1 and x transposed. So just to sort of clarify what I mean, if you've got one data point, the basis phi is 1 and then x. Let's just call it x for the moment. And phi transpose phi is equal to the sum of I equals 1. So this is the matrix phi, the design matrix that we've looked at before. Phi I transpose, yeah? But the n is now 1, and it's made up of just this thing. So that's basically 1x times 1x. So for one data point, that's what that thing is in linear regression. That's a rank 1 matrix. It's a 2 by 2 matrix, but it's rank 1. It's not invertible. So the solution fails when you try it numerically in MATLAB because you try and invert a rank 1 matrix, which is a 2 by 2. Look above. It's still rank 1 for one observation, but you add a diagonal term. This diagonal term makes it full rank. Yeah? Make sense? So this is the prior, this is the regularization over W. And it also keeps W small. It says it works to effect. When you do this solution, if you try these two solutions, as you raise alpha, W will go large. So this keeps the mean of W small. It pulls it towards the prior. In that diagram I shone around of Bishop before, what actually is going on is you've got a likelihood which is something like this, and the maximum likelihood solution is here. And maybe this is a very large value. Then the prior is over here. You multiply the two together, and the solution is pulled towards the prior. As you observe more and more data, this likelihood term becomes smaller and smaller variance. So the solution ends up being pulled back towards the maximum likelihood solution. So another thing that can happen in this solution here is as data goes to infinity, this term becomes very large because it scales with n. It's the sum over n of those basis functions. And this term doesn't change. So this solution is recovered. So in the infinite data limit, or if you make this prior very broad, the solutions are identical. In between, you're adding information which regularizes your solution and can improve performance. And in practice, what we'll often do is fit that parameter by maximum likelihood. So we do maximum likelihood on Bayes, but maximum marginal likelihood, sometimes called empirical Bayes or type 2 maximum likelihood. But don't worry too much about that. OK. Any questions about that bit? Because I think that's important. It's important. And it's something that you should know. It's something you should know why you can't do maximum likelihood when there's fewer data points than parameters in a regression context. And it's something that you should know how Bayesian inference is actually helping you do that. And you should know these formulae and how they relate to each other. Yeah?
So if alpha is very small, then the prior is more infinite.
If alpha is very small, yeah. So in the extreme case, if alpha were 0, that would be like a delta function prior. It would say the weights are 0, and then alpha's 0, and this term's infinite, and the whole thing ends up being 0. So this term becomes infinite, so inverted, it becomes 0, and the weights are forced to be 0. The mean is 0, and when you look at since this is the covariance, right, if this term dominates in the covariance, if this term is very, very small in the covariance, then this term has to be large to overwhelm it. Basically, it just becomes the prior, the posterior inverse just becomes the prior. Sorry, the posterior covariance is just equal to the prior. So it's about this weighting between signal and noise. And remember, well, that's how it's emerging in the solution. But remember, I said there's sort of this interpretation for alpha that it's saying how much signal there is in your data, and this interpretation for sigma, which is saying how much noise. How much of your data is fitting in the model and how much is outside the model. So they've got nice physical interpretations. Not so much for the polynomial basis, because the polynomial basis does lots of ugly things. But for the basis you're using in the lab class, it does. Why not for the polynomial basis? Well, it actually comes, I don't want to go into too much detail because it comes down to this marginal likelihood. You want the marginal likelihood, if you want to know the signal variance, you have to look on the diagonal of this signal term, which for the covariance functions, this is called a covariance function we like to use, it tends to be constant diagonal. For the polynomial basis, it's not a constant diagonal at all, it's a horrible thing. And that explains why if you sample at the start, if you sample a priori, you end up with sort of polynomials always do things like that. In this region here, they're doing something sensible, and then they fly off to infinity. Because as you go outside 1 and minus 1, sorry, that should be the axis in the center there, polynomials blow up very quickly because at 100, x to the 7, 100 to the 7 is a large number. So they behave very nastily, and they're not good things to fit. But we seem to use them as examples all the time for some strange reason. OK, so the last 10 minutes, I wonder if I can do... This is going to be hard because I'm not good at... Well, let's see. Are there any questions there? Any questions?
The difference
maximum likelihood and Bayes method is the prior, I think the prior function, induced prior function. So what is the difference between
the maximum likelihood and Bayes?
And Bayes solution, maximum solution and Bayes solution?
Well, it comes from the prior. So the difference between the Bayesian solution and the maximum likelihood solution, the Bayesian solution is a distribution. And in fact, I should spend a little moment. In fact, maybe I should just explain that a little bit and explain how you get some of these plots. I think there's two things I need to explain for the lab, so maybe I'll do that over the next 10 minutes. The Bayesian solution is a distribution for the parameters. It's not a point estimate. The maximum likelihood. So when we're looking at this thing here, this is the mean of the Bayesian solution. But remember, there's a covariance of the Bayesian solution, which is given by that. Yeah? This term here is the sum term rewritten in matrix form. That's the covariance of the Bayesian solution. So it's got a mean and a covariance. Now, in a moment, I'm going to show you how you use the posterior solution for computing the output of the function, which is what I've just been showing. Yep. Let's forget that for the moment. It's got mean and a variance. Second, the other point you mentioned is the prior. Yes, absolutely, it's got a prior. Now, it is possible, there's a version of an extension of maximum likelihood called maximum a posteriori, which is like a weak Bayesian solution, where you maximize, but you regularize the parameters. And then you get the same, the map solution is actually the same as the Bayesian mean in this case, for this specific case. So you can include priors with the maximum likelihood and optimize, but I'm not covering that. There's a bit about that in the books. So for me, yes, that's a good answer. If you were to be asked in an exam, give the differences between the Bayesian solution and the maximum likelihood solution. The Bayesian solution is a density, a distribution, and to get it, it requires a prior. Whereas the maximum likelihood solution doesn't require a prior, and it's a point estimate. So the fact that it's a distribution, and I think that's the other important point, is what allows us to do these funky plots. Yeah? So these funky plots, what we're showing here is the mean of the function and the two standard deviations either side of the function. So how do we compute that? So that's something that I meant to put in the slides, but I woke up an hour late this morning and didn't get it in. So I'll just do that on the board. So how do we get the mean and the variance? So the two things that aren't in the slide, well, first of all, let's write down, well, one thing that's not in the slides is the maximum likelihood solution, and the marginal likelihood, which we haven't covered how to derive, but you need it for the lab class. So I feel sorry for those that aren't at the lecture, but that's one of the advantages of coming to the lecture. So I've already written this down once, but just to emphasize, oh, sorry, it's a funny K. Is that clear? I'm not sure that bit was clear, but you rewrite that. Where so I forgot the alpha at the beginning of there. It's only taken me 4 weeks to discover that wiping the board off with a wet cloth is a better idea. Yeah, that's the marginal likelihood. Critical thing, that's what you're going to compute. Now, one thing to notice versus the posterior, if we rewrite this posterior using the phi notation as a matrix, so this is, bear in mind, phi is our basis functions, and it's made up of the basis function for each data point in a row vector. So you get this sort of transposition effect, which can be confusing. So each row is a basis from each data point. So in that case, if I write this thing here, this is phi transpose phi. And because phi is a matrix in, if P is the number of features, sorry, N is the number of data points, and P is the number of features. So that means, using the tricks I told you about for matrix stuff, phi transpose is what size matrix?
P plus P.
No! N by N, yes. This marginal likelihood is over T, which is n dimensional, yeah? So phi transpose is n by n, whereas phi transpose phi is p by p. And since this is the covariance of a p-dimensional vector, it better well be p by p, yeah? So phi transpose phi is p by p, and phi transpose is n by n. But notice this guy, oh, I've wiped off the -1. This guy is inverted as well, whereas this covariance isn't inverted. So what actually this is rather nicely, this directly tells you, this covariance thing here, for the signal part, directly tells you the correlation between data points. This matrix, phi transpose. Whereas it doesn't directly tell you the correlation between parameters, because it's got to be inverted, so it's hard to work out. But it directly tells you the correlation between data points. Okay, so that was the one thing I just wanted to cover. And the other thing I wanted to cover is how I did those plots. So I should have had a couple of slides on these things. So can anyone think how I did those plots? Because I went on and on and on and on and on about a posterior distribution over W. And then I plotted uncertainty in the function I was fitting. So what's going on with that? Just to remember, let's say sum of sorry, what am I doing? Well, I'm too used to writing sums. So yi is equal to phi I transpose W plus epsilon. If I have a distribution over W, I can work out the expectation of y if I've got a distribution over W and epsilon. Let's ignore epsilon for the moment and just focus on, sorry, normally we say that's t, but let's just say y is this and focus on this bit, yeah?